When studying infinite series, the main question that we have is whether the series converges or diverges. Remember, if the series converges, that means our infinite sum is equal to a number. If it diverges, this means that it is not a number, and thus there are a lot of things that we cannot do. Over the next few sections, we will be talking about a number of tests that we can apply to series that will tell us whether a certain series converges or diverges. Today, we will be talking about the integral test. To talk about the integral test, I first want to talk about what an integral looks like in terms of the area under a curve. So if we look at this function here, y equals 1 over the square root of x, notice we can draw in these boxes here that give us an area that seems to approximate the area under the curve. In particular, notice the area of this first box is 1. The area of the second box is 1 over the square root of 2. The area of the third box is 1 over the square root of 3. This is 1 over the square root of 4, and so on. And thus, if we add up all of these boxes, we see that this area is equal to 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus 1 over the square root of 4, and so on. And what we see is that we can actually write this as an infinite sum. So n equals 1 to infinity of 1 over the square root of n. Observe that we use left sums here, and thus the area of these rectangles is actually slightly bigger than the area under the curve. And so we see that this definite integral, remember this is an improper integral, 1 over the square root of x dx, this area is going to be less than or equal to the sum of our infinite series, 1 over the square root of n. If we use right sums here, we get a different picture. We see that this first rectangle here is 1 over square root of 2. Second one is 1 over square root of 3, or square root of 4, and so on. So this area is equal to 1 over square root of 2 plus 1 over square root of 3, 1 over square root of 4, and so on. And we can write this as the sum from n equals 2 to infinity of 1 over the square root of n. Notice here that the only difference between the sum and the sum on the previous slide was that we started at n equals 2. And thus we see that this inequality that we can get here is we have our improper integral 1 over the square root of x. This is going to be greater than the sum from n equals 2 to infinity 1 over square root of n. Notice that the inequality in this slide goes the other way than from the inequality in the previous slide. Thus, when we're comparing a series to an integral, we need to be careful about which way our inequality goes. And so this leads us to the statement of the integral test. It says, suppose f is a continuous, positive, decreasing function on the interval from 1 to infinity, and we have some sequence where a of n is equal to f of n. Then this says if our integral, the improper integral from 1 to infinity of f of x dx diverges, then the corresponding series also diverges. And if our integral from 1 to infinity of f of x dx converges, then the corresponding series also converges. Recall how an improper integral may converge or diverge based on the limit that we get. And so thus, if we are able to evaluate this improper integral, we can know right away whether a particular series converges or diverges.